Can you see the presentation? Yes, I think
yes, your screen is just fine. Great. So let me introduce then our next speaker, who is Arley Fernando Torres Galindo from the Universidad de los Andes, Colombia, who will speak to us about ZK Stratifolds. Arley, take it away.
Thanks for the time, but without any kind of introduction for my poster thesis, you can see this poster in the forum. So I want to explain the string root representation problem. It's a nice problem in algebraic topology. The question is if you can represent all manifolds, all homology classes using manifolds. And this is a question. This is the statement for this question. We say that a homological class can be represented by a manifold if you can find a compact-oriented manifold without boundary and a function in such a way that this equation holds. If you know some basic notion of algebraic topology, maybe you can understand this question. In this picture, you can see a pair of homological classes that can be represented by a manifold. The red circle and the blue circle are homological classes that you can represent by manifolds in this sense. And the standard question is, do you can represent all homological classes by manifolds? Some result in this problem is not an easy problem. It's a really, really difficult problem in algebraic topology. And the principal answer to this question is the following. You cannot represent all homology classes by manifolds. And Tom found the first example of a class that you can represent using manifolds. It's a class in this space. This is the product of a length space. There exists some class in this space that you can represent using manifolds, and maybe a general way to deal with this problem is the following. If you know oriented vortices, there exists a natural transformation from this generalized homology theory to singular homology, and the image of this natural transformation is the subgroup of representable classes in the string root sense. There is you can state this question not for the integral coefficients. You can change the coefficients. For example, you can state the same question in singular homology with Cn or Ck coefficients. But this is a picture that represents the idea of vortices, this part. Yes. So stratifold is a topological space with a subsheet of the set of the sheet of continuous functions with some properties. And the idea of a stratifold is that you can generalize the idea of manifold. But the definition is very, very general, so I don't want to give the exact definition of what is a stratifold, but I give an example of a particular stratifolds. They are called P stratifold. And a P stratifold is just a topological space that looks like a CW complexes, but with some kind of additional structure. But basically, we want to know some functions. We call this smart function on this set. And you can see, you can read here the definition. You start with a discrete set of points, and inductively you can boil the another part of the stratifold. You can read this in this part of the poster. Yes. So it looks like a CW complexes is similar in this definition. But the idea is that you can recognize you have a set of functions. You call this the smart function, and you can revolve some well-known facts of differential manifolds, maybe with like a differential plane. You have this set of notion in this set of P stratified. Yes. Maybe a basic example, a manifold and compact-oriented manifold is an example of P stratified. And maybe the first example of an object that is not a manifold is the cone over a manifold. And you can see from this picture how can you build this space. So the cone over a compact manifold is an example of a P stratified. And with these notions, you can build some homology theories that looks like the usual vortices. This is the idea to use this space. So I don't want to give the exact definition for what is a CK stratifold. Just I want to say that a CK stratifold is a stratifold with boundary. Among the other notions that you can recover in this language for these spaces, you can talk about stratifolds with boundary in the same way that you can talk about manifolds with boundary. The basic idea is that stratifolds are a generalization of manifolds, and you can revolve some concepts of manifolds. And you can talk about the stratifolds with boundary. And just a CK stratifold is a stratifold with boundary, and the boundary, you can see the boundary like copies of the same object. You need some orientation. Stratifolds also have orientations, like in manifolds. And maybe the picture is a very nice explanation of what is a CK stratifold. This picture represents a C3 stratifold. It's just a band and some kind of identification in his boundary. And we can talk about CK stratifold vortices. And you can read here the definition, but briefly, a CK stratifold vortices is a stratifold B with boundary, and the idea is that boundary of this subject can be decomposed in this way. It's just like the boundary of B are CK stratifolds and K copies of the same stratifold with boundary. You can glue K copies of the same object and get the boundary of another stratifold. For example, in this case, in the above picture, you glue 3 cups, and then you get the boundary of this of dimension 3. Yes, you can read the exact definition in some paper in Arley. But the geometric idea is, I think, that is clear, and maybe for some of you, some of you know this kind of constructions. And with this, we can do the following. Using CK Stratifold, we can construct an homology theory with CK coefficients. And the idea is just avoid the usual notion of vortices to construct this theory. And just, you can read here again the definition. A singular CK stratifold is just a function from a CK stratifold to a topological space X. We need to impose some conditions in the stratifold. Is the usual condition in this context. And we give the definition of some kind of equivalence relation in these objects, and it's just that this singular stratifold and this singular stratifold are related. If there exists a CK stratifold vortices, and the meaning of this is that the boundary and the boundary in the meaning of the previous definition is equal to this. Yes. And you can extend this function to this pair of functions. You can extend this disjoint union of this function to the inter space V. This is the usual notion of vortices, but with some kind of additional structure, and it's not just for manifolds. We can revolve, we can recover, we can use this same of construction, but using CK stratifolds. And the main result of this theory is the following. We have a natural transformation from this homology theory. This gives us we get an homology theory, but it's an homology theory in this sense. We have a subfunctor.
We have one or two more minutes, just to warn you.
Yes. It's a functor. We have the homotopy action, and we have the major Beatrice sequence. And in this sense, we can give a kind of answer to the Steenrod representation problem. This natural transformation is an isomorphism. The idea is that in this theory, in addition, we can recover the notion of some Bockstein sequence. In this theory, you can see some Bockstein sequence, the usual Bockstein sequence, and we have this commutative diagram in this theory. This diagram is natural isomorphic to the usual diagram in singular homology by means of this natural transformation. And maybe a deeper fact is that you can give an interpretation of the filtration for the spectral sequence of CK vortices. The filtration given by the Atiyah-Hirzebruch spectral sequence gives us a filtration, and this filtration can be explained by these theories. We can impose some natural conditions to get another homology theories. They are natural conditions to get another homology theories. And for these homology theories, we have a natural inclusion. And with this natural inclusion, we can give a geometric description for this filtration. For the last part, but this is not part of the presentation, we can give an stratifold description for maybe some classes that cannot be represented by means by manifolds, and some reference that give a more detail for this topic, maybe a paper or archive and some well-known reference of this kind of problems. Thanks. Thank you very much. This is the last part of the presentation.
Right.
Thank you.
Thank you. Let's thank Arley for a nice talk.
Now you can see this poster at the forum.